Hey guys, if you guys are having problem with your shoelaces falling apart, or if you're trying to learn to knit and you're having a lot of problems with all of these nasty strings, this is the video for you. Today we're going to be talking about constructing suffix arrays, which are powerful tools from computer science to help solve these nasty string problems. We're also going to do it efficiently. In computer science terms, it'll be solved in big O of n log n, where n is the length of the string. What that means is the time to construct this powerful tool called a suffix array is going to be proportional to the length of the string n times the logarithm of n, which is basically negligible. So it's a pretty fast algorithm, and that's important, right? Because computer scientists are very impatient people. Their time is very important. All right, so the algorithm I'm going to give you today, I'll just give you an example and walk through the intuition. And hopefully it'll be very clear at the end why this algorithm works, and you guys will be smart enough to generalize it and write some code for it. All right, cool. So this is the string that we're dealing with, this nasty string that you guys might be familiar with. In the YouTube comments usually, trollolololo, usually more than that. I've cut it short just for your convenience, right? And essentially, just a reminder, suffix array is an ordering of the suffixes of the string, and a suffix starting at index I is the characters of the string starting at I all the way till the end, right? So we want to order these suffixes lexicographically. So to make it easier to work with, we'll actually just convert these characters into numbers, right? Because as you can compare characters, you can also compare numbers, and numbers to me are easier to deal with. And I have done the trouble for you already. I've converted this trololo string into an array A that represents the ordering of the characters using this nice alphabet I have here. There might actually be some mistakes here. I'm not an alphabet expert, but I am a suffix array expert, so that's why you should watch this video. All right, cool. So we have an array A, where we want to sort the suffixes. Intuitively, here's what the algorithm does. Right now, we have an array A, and for example, if we look at the suffix starting here versus the suffix starting here, we know that this suffix A compared to this suffix B, A is definitely smaller than B, right? Because the first character is smaller than the first character of B, so lexicographically speaking, A is less than B. Well, what does this mean? Basically, each number not only represents the ordering of the characters, they also represent the ordering of the suffixes, but only based on the first character of each suffix, okay? So if we can somehow extend this even to two characters, let's say we can compare the first two characters of each suffix. We have an ordering for that. That'll be a step towards our goal, right? Because if we have an ordering of the first n characters of the suffix, that's essentially the problem that we're trying to solve, okay? So let's try to solve the problem for the first two characters of each suffix. To do that, it's pretty simple. We take two characters, right, of the suffix starting at index 0. We get the first two characters, put them over here. We get the first two characters of the suffix starting at index 1 and put them over here. Essentially, we'll list them out, right? We'll list all the tuples out of the first two characters, and now we can sort these tuples, right? Once we sort these tuples, we have an ordering of the first two characters of each suffix. And that's what we did here. The blue numbers represent the ordering after being sorted. So this is the smallest tuple, lexicographically speaking. This is the second smallest tuple. This is the third, but we have two tuples of 1, 2, 1, 2, right? So, we don't know which one is bigger because it's kind of ambiguous. So ambiguous based on the suffix, that is, right? Because this represents the first two characters of the suffix, and this represents the first two characters, but we don't have the rest of the characters. So we'll just label them as both 2s. And the same we'll do with 3, right? And then this is clearly bigger than all of that, and this is clearly the biggest, right? So we have an ordering, and we copy the ordering over, right? So 5, 4, 3, 1, 2, 3, 2, 3, 0. Right? So look at this array. This array here represents the ordering of the first 2 characters of each suffix. Pretty cool, right? We're a step closer to our goal. Now, let's try to extend this idea. The reason we could calculate the ordering of the first 2 characters is because we grouped them, right? And we grouped them and we just did a sort. We can sort of do the similar thing, but now for the first 4 characters, let's say we want the first 4 characters of the suffix, right? How do we represent that in an ordered way and using the information we have? Well, I claim it's sufficient to take the first and the third number in this new array and put it into a tuple. Essentially now, instead of putting consecutive numbers, we put tuples separated by 2's, right? And that's essentially because this number already represents the ordering of the first 2, right? And this represents the ordering of these 2. So if we put them together, it represents an ordering of all 4, right? So we continue in this fashion. We get these tuples, right? And this is the important stage, constructing these tuples, right? Because once we constructed these tuples and understood that 5, 3 together represents the ordering of the first 4 tuples, over the first 4 characters of this string, and 4, 1 represents an ordering of the 4 characters starting at the suffix of this index. So 3, 2, 1, 1, this suffix is represented by 4, 1. That's the core idea, right? Now we have this array of tuples. We sort it again, and these are the indices after sorting, and we copy them over just like last time. And we get this ordering. So just like how this array was an ordering of the first 2 characters of each suffix, this array, A4, is now an ordering of the first 4 characters of the suffix. And let's notice something great here. Notice that all of these numbers are actually unique. What this means is that there's no ambiguity here. All the suffixes are sufficiently compared using their first 4 characters. That's great, right? That means we can terminate now, because essentially we have a unique ordering of the first 4 characters of each suffix. So lexicographically speaking, we have a unique ordering among the suffixes. And that's how we construct the suffix array, right? Because you look at the smallest ordering of the first 4 characters, that's 0. So that's the index 8, and that's over here. And the second highest is 1, and that's index 3. We place it here. 2, that's index 6, and so on. So after this, we construct the suffix array. And just for a sanity check, because I could make mistakes, even though I am an expert on suffix arrays, I've written down the suffixes, and it looks right to me. So to do a runtime analysis, note that we started off with a block size of 1. What I mean by that is that we had an ordering amongst the first character of each suffix. And then we had an ordering among the first 2 characters and the first 4 characters, right? And notice that there's a pattern here. The next one will be 8, and the one after that will be 16. So you keep multiplying by factors of 2, and it's growing in an exponential manner. So what does that mean? That means the total number of iterations that we have to do until we're guaranteed a unique ordering where each number represents the ordering of the first n characters of the suffix, right? The number of iterations until we have that is big O of log n. And at each layer, we perform a sorting, right? And that's going to dominate our cost. We perform a sorting. If you use merge sort, which takes O of n log n, we get this down, right? Which is, so the overall runtime would be n log squared n. But we can do better using this concept called radix sort, which actually sorts in big O of n because we know that these numbers are bounded. Since we know that, we actually get an overall runtime of big O of n log n. That's pretty great, right? We can construct this powerful tool to help you solve all of your string problems in just big O of n log n. And there you have it, folks. We have an algorithm a very intuitive algorithm for constructing the suffix array by coalescing based on blocks and comparing and expanding these block sizes until you compare and have a global ordering among the whole string. There you have it, folks. Thank you for listening and have a good day.